Now let us talk about pulmonary circulation. Normally a low resistance high compliance system, okay, this pulmonary circulation is a high compliance system because there is very low resistance compared to the systemic circulation. And PO2 and PCO2 exerts opposite effects on the pulmonary and systemic circulation. For example, in systemic circulation there will be vasodilation, but in the pulmonary circulation there is hypoxic vasoconstriction that shifts blood away from the poorly ventilated region of the lungs to the well ventilated region of the lung. This is very well known fact, isn't it? Now talking about the perfusion limited and diffusion limited circulation. So just remember, if there is no diffusion limitation, okay, and then it is certainly it can be perfusion limited. For example, to be diffusion limited, there should be problem in diffusion. For example, in emphysema or fibrosis. Okay, these are the condition where there is problem in diffusion. But perfusion limited can also convert into diffusion limited condition in case of exercise. Okay, so in exercise there is limitation in diffusion as well. Okay, and talking about the example, you can see oxygen, carbon dioxide, and nitric oxide. So but oxygen in normal health is perfusion limited compared to the oxygen in disease state, that is emphysema, exercise, and fibrosis. Okay, and also the carbon monoxide is diffusion limited. Gas does not equilibrate by the time blood reaches the end of capillary. Here you can see the thing that I just said. Okay, let's see the oxygen. Okay, now oxygen will equilibrate. This is the length of pulmonary capillary, and the oxygen concentration will equilibrate very comfortably in the, you see, in the middle, okay, or in the beginning. So this is perfusion limited. Now in the cases of diffusion limited, it is not equilibrated even at the end. You see, it's not equilibrated. The graph is rising, and it is not being equilibrated. Whereas in cases of normal state, the oxygen is perfusion limited. Okay, so it can easily get equilibrated. The alveolar and arterial side, the partial pressure gets equilibrated very early. Okay, but in cases of fibrosis and, as I said, emphysema, there is diffusion limitation. Okay, also carbon monoxide is a diffusion limited gas. Okay, independent of the disease. Gas does not equilibrate by the time the blood reaches the end of capillary, as I said. Now talking about what are the consequences of pulmonary hypertension. Pulmonary hypertension can cause cor pulmonale. Okay, cor pulmonale is right ventricular failure that is dependent on the lung causes, be it lung parenchyma, lung vasculature, or chest wall. Okay, this is the definition of cor pulmonale, if you remember from your high school. Now diffusion, and this formula is very relevant. Diffusion is directly proportional to the area, and that is logical, isn't it? Area and diffusion constant and the partial difference in the partial pressure. Okay, so the more area, there will be more diffusion. Now think about the disease that can affect these parameters. For example, if the area is decreased, such as in emphysema, then there can be decreased diffusion, and that is why there was diffusion limitation in the case of emphysema. Thickness can increase in pulmonary fibrosis, and you see, if the thickness is increased, this thing called delta X, if this is increased, diffusion will be decreased, isn't it? Because it is the inverse relation. Now that's in the case of pulmonary fibrosis, which we talked about in the diffusion limited case. So DLCO is the extent to which carbon monoxide, a surrogate for oxygen, passes from air sacs of the lungs into the fluid. So DLCO will decrease in the condition, okay, where there was defect in the diffusion, for example in pulmonary fibrosis and emphysema. Okay, Now talking about the pulmonary vascular resistance. What is the formula of pulmonary vascular resistance? It is simply the difference in it is just like the V equals to IR formula in the electricity. Okay, so remember, R is equals to the V by I, isn't it? I is the flow, so cardiac output is kind of flow, and P is like voltage, difference is voltage, so that is pulmonary pressure, and this is left atrial pressure, the difference. Okay, now resistance is also equals to 8 sigma L over pi R to the power 4. So here you can see that this sigma is viscosity of the blood, L is the length. So length, in increase in length there will be increased resistance. If the blood is thicker, for example, let's say polycythemia or multiple myeloma, where the blood is thicker, that can lead to the more resistance. Okay, and if the radius, it is inversely related, the more radius there will be less resistance. Okay, now talking about the alveolar gas equation. Partial pressure alveolar PO2, okay, PaO2 is equals to PiO2 minus PaCO2 over R, where PaCO2, actually PaCO2 over R is equal to PaO2. If you see in this formula that R is equal to respiratory coefficient is equal to carbon dioxide produced over oxygen consumed. Okay, so just think about it. So if you try to calculate oxygen consumed, then oxygen consumed will be equals to PCO2 over R. If you just do some arithmetic adjustment, there will be like O2 consumed will be equals to CO2 over R. Okay, and that is what they have written here, PiO2 minus arterial CO2, arterial O2. Okay, arterial O2 you can find out by PaCO2 over R, and that is why there is 150 minus 150 minus, which is PiO2, this is the atmospheric pressure if you are breathing at sea level, and PaCO2 over 0.8. Okay, now AA gradient is equals to PA2 minus PO2. Normal AA gradient is estimated by age by 4 plus 4. For a person less than 40 years old, gradient should be less than 14. AA gradient more than 15, BQ mismatch, think of BQ mismatch pathology or impaired diffusion. Okay, one thing that I have added here is pulmonary vascular resistance. Two vessels, alveolar and arteriolar, increase in lung volume stretch alveolar vessel makes them longer, and smaller diameter increases the resistance. Okay, and decrease in lung volume narrow the arteriolar vessels, which increases the resistance. Okay, next page. Now talking about the oxygen deprivation. It can lead to hypoxia, hypoxemia, or ischemia. Hypoxia is when there is decreased O2 delivery to the tissue. It can be either due to cardiac output, decrease in cardiac output, hypoxemia, anemia, or CO poisoning. Okay, anything can lead to decreased O2 delivery to the tissue. Now hypoxemia is basically a decrease in partial pressure of oxygen, could be divided into normal AA gradient to increase in AA gradient. Now when there is normal AA gradient is high altitude, hypoventilation, for example opioid use. I want to add here that in opioid use there is irregular pattern of respiration. Okay, obesity and hypoventilation. Now think about it. See, AA gradient will increase only when there is any defect in the diffusing membrane. Okay, so here in normal AA gradient, it is just that there is less PO2 being absorbed. Now in increase in AA gradient, what happens? Oxygen is getting into alveoli, but from alveoli it is not getting into the blood compartment. Okay, so here you can see increase in AA gradient, that is more than 15, can be occur in the VQ mismatch. Okay, diffusion limitation, for example fibrosis, and also if there is right to left shunt. Now think about it. In right to left shunt, what happens? In right to left shunt, the blood get Okay, the blood gets shunted from the right side to the left side without being oxygenated. Okay, so that is one reason where there can be hypoxemia with increase in AA gradient. AA gradient normal value is 5 to 15, don't forget that. Okay, and ischemia is loss of blood flow, for example impaired arterial flow or decrease in venous drainage. Now let us talk about ventilation perfusion mismatch. Okay, this is very 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 easy. Okay, don't try to make it complicated, please. Okay, don't try to make it complicated. What happens here, I will talk in a very simple way. Everything, okay, if upper like V by Q, in V by Q formula, okay, uh, V by Q, both thing will decrease in apex. Think about it. Ventilation is also decreasing in the apex, and also the perfusion is decreasing in the apex. But finally, V by Q ratio becomes high. Now you can adjust the numbers. Okay, so to increase the V by Q, you have to decrease the denominator in a very high amount. Okay, if you put a double arrow down, then the whole ratio comes out to be high, isn't it? So this is the thing, just remember everything decreases, all the parameters decreases in the apex, but the final result will be high. But reverse this condition in the zone 3, there will be increase in ventilation, increase in perfusion, but final result comes to be low. And to do this, we have to increase the denominator, and this is very simple way to calculate this and not get trapped by the complexity. Okay, so ideally ventilation is matched to perfusion, that is V by Q equals to 1 for adequate gas exchange. Lung zones, V by Q at apex of the lung is 3, wasted ventilation. Okay, because perfusion is very 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 low compared to the decrease in ventilation. Though ventilation is also decreased, but perfusion is decreased so much so that the ratio comes out to be high. Okay, with exercise in okay, V by Q at base is 0.6, that is wasted perfusion, where perfusion is far higher than the increase in the ventilation, you can see over here. Okay, so that will bring the final result to be low. Okay, so both ventilation and perfusion are greater at the base of the lung than the apex of the lung. With exercise, increased cardiac output, there is vasodilation of the apical vasculature, and V by Q ratio approaches to the 1. Okay, so just imagine V by Q ratio was around 3 at the apex. Okay, but as with exercise it approaches the value 1 because of the vasodilation. Certain organism that thrives in high oxygen, for example TB, flourish in the apex. V by Q ratio is equals to 0 if airway obstruction, and that is logical because V will be 0. And V by Q can be infinity when blood flow obstruction, that is physiological dead space, because Q will be 0. So anything divided by 0 will be infinity. Assuming less than 100 dead space, 100% dead space, 100% oxygen improves PaO2, example in the pulmonary embolus. Okay, now I want to add something about this zone. Okay, different types of zone. This is very very easy actually again. Okay, so here what happens, that arteriolar arteriolar partial pressure is more than the alveolar pressure is more than the arteriolar pressure. Okay, capital A is alveolar, so alveolar pressure is more than the arterial in zone 1. Okay, then if just imagine if the alveolar pressure is high, what will happen to the lumina of the artery? It will be collapsed, isn't it? So so that leads to the collapsing of the capillary, and there is no blood flow. That is in zone 1 represents alveolar dead space. Okay, because there is no blood flow in the zone 1. This region can form when there is low pulmonary arterial pressure, for example in heavy hemorrhage, or high alveolar pressure as in positive pressure ventilation. So in two condition, so how can you increase the alveolar pressure? By positive pressure ventilation. Or how can you decrease the arteriolar pressure? By heavy hemorrhage. Okay, these two things can lead to the zone 1 formation. Now talking about zone 2, zone 2 is again simple, found in higher area. Arteriolar pressure is more than the alveolar pressure. which is more than the venous pressure. Okay, now simply the arteriolar pressure is being, see in this, how to remember this very easily. The alveolar pressure was first in zone 1, but it becomes second in zone 2, and it becomes last in the zone 3. That is how I remembered. Okay, so basically zone reminds you of the position of the artery, alveolar. Okay, alveolar, and arteriolar is always bigger than the venous side, so it is very easy to remember that way. Okay, I want to repeat it. Zone will remind you of the position of the alveolar. Okay, in the hierarchy. That is, in zone 1, alveolar pressure will be high. In zone 2, alveolar pressure will become second, and in zone 3, alveolar pressure will be the least. Now talking about zone 2, found in the higher area, the arterial pressure is more than the alveolar pressure, which is more than the venous pressure. Because alveolar pressure is greater than the venous pressure, the pulmonary capillaries are initially obstructed near the venous pressure, near the venous end of the capillary bed. However, as the arterial pressure rises during systole, so capillary pressure becomes high enough to overcome the alveolar pressure, and blood flow through zone 2 in the pulsatile fashion. This is very important. Okay, and it is logical also. Okay, because here it will be pulsatile fashion. Now in zone 3, arterial and venous pressure are both greater than alveolar pressure. As I said you that every zone reminds you of the position of the alveolar pressure. In zone 3, alveolar pressure will be third compared to the arterial and venous. Arterial will be first, venous will be second as usual, and alveolar pressure will be third. And therefore blood flows continuously throughout the pulmonary capillaries. When a person lies supine, differences in the lung perfusion are negated as gravity then affects the lung equally from the apex to base. In the supine individual, the lung is entirely zone 3. Okay, so that is why I have drawn this cartoon where the guy is lying, okay, supine, and that is how and you can see it is structured into 3. I think it is girl. Okay, and that should remind you of the zone 3. Okay, this is very important. Here is the same thing that I have represented in a different picture. You can see the BQ was 2.5, which is high at the apex, but it can approach to 1 with exercise because of the vasodilation, as I said to you, right? So now next page. Now this is the last page of the physiology, so that's why I wanted to complete everything here. Okay, so this is very easy. Okay, carbon dioxide is transported from the tissue to the lungs in 3 forms. One is bicarbonate form, which is 70%. Carbaminoglobulin, okay, that is again 21 to 25%, and dissolved is the least amount. Now here in the image also you can see that the most of the carbon dioxide is getting inside the RBC, which will later you will see converted into bicarbonate form, isn't it? And this bicarbonate will exchange with the chloride for electric neutrality. That bicarbonate will leave the RBC and chloride will come inside to maintain the electric neutrality. Okay, just remember that chloride will shift inside, and this is very important point again. Okay, and this is the maximum, number 1. You see, 70% of the carbon dioxide travel in this fashion. Now second rank is for the carbamino hemoglobin, that is the carbon dioxide binding with the hemoglobin. So that is in the second rank. You can see the line becomes thinner, and it is more thin in this side. It should have been more thin because it is the least. You see, 5 to 9% getting dissolved. Okay, this is the least one. So here you can see in the lungs, oxygenation of the hemoglobin promotes dissociation of the H plus from the hemoglobin, thus shifts equilibrium towards the carbon dioxide formation. Over here you see this after the bicarbonate breaks into H plus and bicarbonate. Okay, carbonic acid is broken down into H plus and bicarbonate. Bicarbonate will shift with the this chloride, exchange with the chloride, but this H plus will bind with the hemoglobin. Okay, now this is the tissue side, but when it gets into the lung side, this will dissociate back into H and H plus. Okay, you see in the lungs, oxygenation of hemoglobin promotes the dissociation of H plus from the hemoglobin. This shifts the equilibrium towards the CO2 formation, and at this time, this reaction will be more favorable. That by carbonic acid will be, forming the carbon dioxide. Okay, carbon dioxide, so that this carbon dioxide can get into the lungs and exhaled out. In peripheral tissue, increase H plus, okay, increase H plus from the tissue metabolism shifts the curve to the right, unloading the oxygen. That is the Bohr effect. Okay, so what happens in the peripheral tissue? See, peripheral tissue, what happens? This H plus will bind with the hemoglobin and displace the oxygen. Okay, displace the oxygen so that it can go into the tissue where it is required. So this I have simply to remember, it betrays the oxygen in the H plus rich area. That is for the Bohr's effect. B for betrays, O for oxygen, in H for hydrogen, R for rich. So it betrays the oxygen in the H rich areas. So this is basically the story of the Bohr's. So basically Haldane effect occurs in the lung side, but Bohr effect occurs in the peripheral side. This is very, very important concept, and don't forget about this chloride. They make silly question on this. Okay, I've written here, erythrocyte in venous blood has higher chloride content, and it is logical. You see, erythrocytes, this is the whole thing is the erythrocyte has higher chloride content, obviously, because it is pushing the bicarbonate with the exchange of the chloride. So that is the thing I wanted to ask, and this is a question in the UWorld. Now talking about different response in to high altitude, what happens to the different altitude parameters? See, first of all, the atmospheric oxygen, okay, atmospheric oxygen will decrease, inhaled partial pressure of oxygen. So that is why there will be decrease in the partial pressure of arterial oxygen, and there will be increased ventilation. Increased ventilation will wash out all the carbon dioxide, and this is the reason for the respiratory alkalosis, which is responsible for the altitude sickness, that is headache, okay, insomnia, all those things is because there is respiratory alkalosis. Now talking about chronic increase in ventilation, okay, obviously the body tries to maintain the oxygen by ventilating in higher rate, and it also increases the pulmonary diffusion capacity. Now hypoxia can trigger the hypoxia inducible factor, which will lead to the formation of which will trigger the formation of erythropoietin from the interstitial cell of the kidney, and then there will be more erythrogenesis. So that is the reason for increased hematocrit and hemoglobin due to chronic hypoxia. Now there is also increase in 2,3-BPG, which is also seen in exercise, which shifts the oxygen dissociation curve that I explained earlier to the right side. Okay, cellular change, there will be increase in the concentration of mitochondria, and there will also be increased renal excretion of bicarbonate to compensate for the respiratory alkalosis, and can augment with the acetazolamide. So this is basically our body physiology, which leads to peeing out all those bicarbonate, because the body is in the alkalotic state. Okay, so there is high bicarbonate in the body, and the body will adapt this change by increasing the renal excretion of bicarbonate to compensate for the respiratory alkalosis, and can augment this physiological phenomena by giving acetazolamide. So I just want to remind you that whenever we used to go for mountain climbing or hiking, okay, we used to have some acetazolamide tablet with us, and this was the reason. Okay, so chronic hypoxic pulmonary vasoconstriction result in pulmonary hypertension and right ventricular hypertrophy. So they might ask you what is the changes in the right ventricle during the high altitude. There will be right ventricular hypertrophy. This is very, very, very important. Why? Because your right ventricle has to work overtime to overcome the pulmonary hypertension, which is causing the resistance to the outflow of the right ventricle, right? Also there will be increased production of VEGF, which induce the angiogenesis. Now response to exercises increases the carbon dioxide production, increases the oxygen consumption, and increase ventilation rate to meet O2 demand. VQ ratio from the apex to base becomes more uniform. Increased pulmonary blood flow due to increase cardiac output, decrease pH during strenuous exercise, obviously logical because of the secondary lactic acidosis, but remember this is only in the strenuous exercise. Okay, the pH will not change in moderate exercise. It only happens in the strenuous exercise. This is very important point. Remember, there is no change in PaO2 and PaCO2, but increase in the venous carbon dioxide content and decrease in the venous oxygen content. So be very careful while choosing your option, because this is very important, and that the patient and the student might get lured by the options in the arterial side, but arterial content of oxygen and carbon dioxide is not changed. Okay, it's only the venous side that is changing. Increase in venous carbon dioxide content and decrease in the venous oxygen content. Okay, so here I have also said that vein change. Okay, this is basically nothing but the a question in high altitude, what was the change. So remember, I said you in high altitude there is hyperventilation. So what will happen to the pH will be high, isn't it? And PaCO2 will be 20 and PaO2 will be 60. Okay, and obviously why the PaCO2 is changing? Because of the hyperventilation. Okay, bicarbonate is increasing or decreasing? Decreased. Okay, why? Because renal compensation has started working because the time frame is 2 days. Okay, and remember that the renal compensation starts working during the time of 24 to 48 hours. Hypoxemia persists because the low PiO2 allows hyperventilation to increase PO2 only slightly. So hypoxemia can still be there. Okay, hypoxemia can still be there. So basically there is hypoxemia, hypocarbon dioxide because of the hyperventilation, and also there is decrease in the bicarbonate level. So basically in 2 days everything is decreased. You notice that PO2 is still decreased because of the inhaled oxygen has low partial pressure of oxygen. PaCO2 is decreased because of the hyperventilation, and bicarbonate is decreased because of the renal compensation, which is renal peeing out of the bicarbonate. And tell me the drug which can augment that. Very good, very good, acetazolamide. Okay, carbonic anhydrase inhibitor. Now one question: stuck in elevator, hyperventilation, hypocapnia, decreased cerebral perfusion. This can lead to generalized weakness, blurred vision, pre-syncope, dizziness, lightheadedness, and syncope. Okay, so this is a classic case of hyperventilation leading to respiratory alkalosis. Okay, so this was it for physiology of respiration. Now in the next video we will continue the pathology and discuss all the different diseases that we can see in the respiratory system. Okay, thank you very much. See you in the next video.